excuse me.
Oh, hi.
I'm looking for the Liberty Bell. Could you please help me?
Oh, you're lost? Don't worry, I can help you be found. Take a seat, and let me tell you the epic, true, and currently unfolding story of Omar Yagi, Moth 303, and the future of humanity.
Okay, sure. I love true and currently unfolding stories. Who is Omar Yagi? What the heck is a moth? And what does this story have to do with humanity? Something I'm currently a member of.
I'm so glad you asked.
And let me tell you about a scientist named Omar Yagi and his marvelous invention that could save the world. No, this isn't a joke or a fairy tale. Omar Yagi is one of this year's Nobel Prize winners in chemistry. He is a scientist born in Amman, Jordan, to his parents who were both refugees from Palestine. Today, he sits as the James and Nigel Tretter Professor of Chemistry at the University of California, Berkeley, one of the most distinguished honors a chemist can receive. He is widely recognized as the founder of his field of reticular chemistry, and he earned his Nobel Prize in recognition for his synthesis of a metal-organic framework called Moth 303.
Wow, Omar Yagi sounds like a serious scientist. But what is a metal organic framework, and how is this thing gonna save the world? Save the world from what?
Shh, don't fret. Scientists like Omar Yagi and his accompanying winners, Richard Robson and Susumu Kitagawa, are kind of like superheroes, fighting threats that most people don't even realize we're facing. For example, did you know that 4 billion people, almost 2/3 of the world's population, experience severe water scarcity for at least 1 month each year? And UNICEF predicts that by 2040, roughly 1 in 4 children worldwide will be living in areas of extreme water stress.
Things like droughts, which are exacerbated by climate change, contamination, overuse, misuse, and technological advancements like AI all contribute to this growing problem of water scarcity at an alarming rate.
If Omar Yagi's our superhero and water scarcity is our threat, then science is our hero's superpower. And his son, Omar Yagi's Moth 303, might just be the secret weapon needed to save the world. Let me elaborate.
Metal organic frameworks can be broken down into singular units consisting of 2 vital parts: a metallic center surrounded by organic ligands. The metallic center usually consists of a cluster of metal atoms, typically something like aluminum, cobalt, copper, etc. And these clusters are surrounded by organic molecules, the ligands, which connect to the metal center in a specific and highly ordered way, kind of like branches of a tree, except they're not really branches, they're actually more like bridges. They connect one metal center to another, and one identical unit connects to another, and another, and another, and another, until you're left with this solid and rigid crystalline complex.
What's interesting about these structures is that they leave behind these big open spaces, kind of like scaffolding. No, wait, exactly like scaffolding. Here's a picture of a scaffolding outside of some old chic building. If you look here, these corners are just like the metallic clusters making up the outline of the scaffolding. The poles are acting like organic ligands, connecting all the corners to complete the 3-dimensional structure. This specific scaffolding is set up to help builders reach different parts of the building. So in the open spaces left by the setup, there are these wooden panels so that the workers can stand there and do their job. It's the scaffolding's framework that allows for these perfectly sized open spaces that fit the panels and the workers, and overall give the scaffolding its function. Metal organic frameworks work just like this, except they're way smaller, and instead of wooden panels and builders, they're engineered to catch specific chemicals or molecules in their open spaces. Here's a real-life example or model of what a moth looks like. You're currently looking at a complex called HKUST1, which our lab attempted to synthesize earlier this fall. The red atoms represent the metallic copper-2 clusters, while the gray are the organic ligands. You can see how the repeating units link together to form the larger structure. Notice the circular holes or pores in the middle of the crystalline solid. Here, 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 and so on. See, in recent years, and largely due to the contributions of Yagi, Robson, and Kitagawa, scientists have learned how to carefully manipulate the exact size and shape of these empty pockets left in the metal organic frameworks down to the molecular level, using highly specified metal ligand combinations.
Oh, okay. I think I understand. But how can moths be used to save the world?
Well, Omar Yagi, along with Robson and Kitagawa, are credited with the creation of Moth 303. What's so special about this moth? Well, the pockets of MOF 303 are perfectly sized to fit water molecules. That means if you stuck some MOF 303 into a puddle of water, it would act as a sponge, sucking up water molecules into the open spaces within its structure.
Okay, so he made a fancy metal sponge. I'm still not seeing how this will save the world.
Okay, attitude, hold your horses. I was getting there. I can assure you, MOF 303 isn't just some fancy metal sponge. See, if you took a regular old sponge and set it out on a platform in the middle of a desert with no rain, you wouldn't expect that sponge to absorb any water, would you? And if you were to collect your sponge, say, a week later, assuming it still hadn't rained, it wouldn't hold any more water than it did before you first put it there, right? MOF 303 is no ordinary sponge. It's not even a sponge technically, it just acts like one. I digress. The special and award-winning facet of MOF 303 is that when it's left out in one of the driest deserts, Silicon Valley, no rain, it was able to harvest at a capacity of 210 and 285 grams of water per kilogram of MOF per day.
According to a paper published in July 2023 in Nature Water.
Yeah, try to make your crusty old kitchen sponge do that.
Wow, wait, really? It was able to collect water out of thin air? That really does sound like magic. How does it work?
Well, in order to properly explain that, we're going to have to break down the science, young traveler. First, let's talk about the chemistry of MOF 303, and then we can talk about how it works in practice.
Everything I'm about to tell you is sourced directly from the original paper published in Science Advances Journal by Omar Yagi's lab in October 2022.
You're looking at an image taken directly from the original paper from Omar Yagi's lab. In this image, gray is the carbon, green is the nitrogen, red is oxygen, and blue is aluminum. This image breaks down the synthesis of MOF 303 to a relatively simple reaction. There are some fundamental principles that we've discussed during this semester of my inorganic chemistry course that can help us understand why MOF 303 does what it does. For example, we could understand some of the rationale behind their choice to use this specific metal-ligand combo by considering hard and soft acid-base theory. Aluminum 3+ ions in this complex, pictured in blue, act as a hard acid, while the carboxylate groups, pictured on the ligand, act as a hard base. Since they're both on the harder side of the respective Lewis designations, they create a really strong and really stable ionic backbone, which is crucial to the function of the MOF.
Wait, but I wasn't even in your inorganic chemistry class.
I wasn't finished. Earlier, I was telling you how they cleverly engineered MOF 303 to collect specifically water molecules. It sounds so much easier said than done. There's so many different types of molecules in the air. How did they ensure that only water molecules were being captured by the MOF and not, say, N2 or CO2?
Okay, so now you're just asking all the questions?
Hush, stop fretting. I will tell you. As I mentioned before, they engineered the size of the entrance of the pores. In MOF 303, they're exactly 6 angstroms in diameter.
What is an angstrom?
The size of one water molecule is approximately 2.75 angstroms. Great, it fits. Well, what about all the other common air molecules that are smaller than 6 angstroms? For example, an N2 molecule is approximately 3.6 angstroms, and one molecule of CO2 is approximately 2.4 angstroms. How do they stop those molecules from absorbing onto the MOF?
Well, in order to bypass this issue, they had to make sure to select ligands that have a high affinity for water. Take another look at the structure of the ligand they use in MOF 303. We already talked about the significance of the carboxylate groups being useful for the strength of the backbone. The nitrogen-containing pyrazole ring in the center of the ring was also an intentional choice. Each of the nitrogen atoms in this ring has a purpose that ultimately allows for MOF 303 to be highly selective for water. The nitrogen on the right is a strong hydrogen bond acceptor, and the nitrogen on the left is a hydrogen bond donor. This attractive force is what brings water molecules in initially, as they H-bond first to the ligand and then to each other, as water molecules are known to do. Of course, there's some other measures in place to encourage only water to bind to MOF 303, but the manipulation of the size of the pores as well as the H-bond availability are two major factors that contribute to this MOF's hydrophilic quality.
As for the practical application, that can be simplified and broken down into 3 steps. The water cycling process starts at night, when the humidity levels are usually higher. The absorption of water onto the moth is driven by something called a chemical potential gradient. Basically, the chemistry of the moth makes it so that it's always trying to reach an equilibrium with the surrounding atmosphere with respect to water concentration. Even if there are very few water molecules around, this fundamental and spontaneous process will cause at least some water molecules to stick to the moth. The following morning, the moth is placed inside a closed container and gently heated using sunlight. The sunlight provides just enough warmth for the hydrogen bonds holding the water onto the moth to break, which is then released as pure water vapor into the small container. The water then condenses on the walls of the container and eventually collects at the bottom as pure, drinkable liquid water.
Wow, this is truly amazing technology. It makes me so hopeful that chemists like Omar Yagi are using their power to help people facing water scarcity all around the world.
I agree. I shared this story with you because it is a powerful one. One man from humble beginnings was able to persevere through adversity and prejudice to dedicate his lifelong career not only to advancing science, but to leaving the world a better place than he found it. And I hope to do the same with my career one day. Oh, and traveler, the Liberty Bell is that way.